We have made it to the last lesson of the term, and what we are going to do today is prove the fundamental theorem of arithmetic, the statement that tells us that if we have a positive integer greater than 1, then it factors uniquely into a product of primes. And so that's the goal for today, but once we prove the fundamental theorem of arithmetic, we are going to be able to prove that if n is some integer that is not a perfect square, then the square root of n is always going to be irrational. And this will generalize the notions that we have discussed in the beginning of the term. We saw that the square root of 2 was irrational. For the first midterm, you proved that the square root of 3 was irrational. Well, today we'll have that the square root of n is irrational for every integer that is not a perfect square. So let's go ahead and get started. The first statement we covered last time, and it is the notion of what it means for two integers to be relatively prime. Something to note is that Bellman says everything in the context of positive integers. All these definitions hold for the integers as a whole, and so I've gone ahead and crossed out the part where he says positive. So given two integers a and b, and their GCD is equal to 1, then we say that a and b are relatively prime. And the first statement we are going to prove today is Theorem 7.2.2, which tells us that for all integers a, b, and c, if c divides a times b, and the GCD of a and c is equal to 1, then c must divide d. So how do we prove this? Well, we are going to use Bezo's lemma. And so, in this situation, we have that a and c are relatively prime. So let us go ahead and get started. So here we have integers a, b, and c, such that c divides a times b, and the GCD of a and c is equal to 1. And now by Bezo's lemma, what we get is that there exists integers x and y such that a times x plus c times y is equal to 1, since 1 is the GCD of a and c. And so we got this here. But where do we go from this? We got this equation ax plus cy equals 1, but what we know is that c divides a times b. And so what we are going to do now is multiply both sides of this equation by b, because in doing so, we are going to introduce an a times b here, and then we have that condition that c divides a times b. So let's go ahead and do that. So multiplying both sides by b yields that we have abx plus cy is equal, and now we have b. But now we have that c divides ab. So c divides ab, and c of course divides c times y. So now we got the linear combination lemma. And so by the linear combination lemma, we get that c divides b, since c divides ab, and c divides c times y. But that is what we wanted to prove. We wanted to prove that c divides b, and so that finishes it off for this proof, QED. And so we are done with the proof of Theorem 7.2.2. And now we get to the famed Euclid's lemma. So Euclid's lemma, as it appears in Euclid's Elements, states that for all integers a, b, and p, where p is a prime number, if p is prime and p divides a times b, then either p divides a or p divides b. So let's prove this. So that p divide a times b, and then if it is the case that p divides a or p divides b, then there's nothing to show, since that's what the conclusion is. And so now what we are going to do is suppose that p does not divide a or p does not divide b. So recall from chapter 3, whenever we want to prove a conditional that has a consequent as a disjunction, in this case p divides a or p divides b, then we may assume that one of them doesn't hold and show that the other one must hold. And that's exactly what we are going to do just now. So we have p does not divide a or p does not divide b. So with all loss of generality, we may assume that p does not divide a. But if p does not divide a, that means that the GCD of a and b must be 1. And so we have the GCD of p comma a must be 1. Because the divisors of p, since p is prime, are going to consist exactly of 1 and p. And the divisors of a, there could be many. But we know 1 is a factor, but p is not a factor of a, since p does not divide a. And consequently, the intersection of divisors of p with the divisors of a must consist of exactly the element 1. And so we get that the GCD of a and p is equal to 1. But now we are in the setting of Theorem 7.2.2. Because Theorem 7.2.2 tells us that if we have in integers a, b, and c, where now c is p for it in the setting of 7.2.3, so we have p divides a times b, and we have that the GCD of a comma p is 1. Then Theorem 7.2.2 tells us that p divides b. And so by Theorem 7.2.2, we get that p divides b, which concludes the proof. And we're done. We have now gotten Euclid's lemma. Now, something to note in terms of history. Euclid's lemma dates back to 300 of the Common Era. Now, the way that we went about this was by using Bezout's lemma, which came about in 1624. So, this is not the proof that Euclid gave. The proof that Euclid gave for proving Euclid's lemma was rather involved, and it required several uses of the well-ordering principle to derive a contradiction. We have had it easy in that by having Bezout's lemma, we are able to prove this without that much effort. But in our last lesson, when we proved Bezout's lemma, we relied on the well-ordering principle to prove the statement. And so that is already hidden inside the proof for the Euclid's lemma that we just did. It also follows a similar thought process to that which Euclid gave, just that by having Bezout's lemma already take care of the argument via the well-ordering principle, we don't see that aspect of it in the proof. So now that we have this statement, we can generalize and then consider the situation where we have a prime number p that divides a1, a2, all the way to ak. And if p divides the product, then there is some index I such that p divides one of these a sub j's. So let's prove this. And we're going to do induction. So let s of n, or in this case, let s of, for each. So for each positive integer k, let s of k be the statement if P divides A1, A2, dot 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 to AK, where each A sub j is an integer, then P divides A sub j for some index j in the set 1 through k. And so one of these must be the case. So let's go ahead and do this by induction. So we proceed by induction on k. If k is equal to 1, then P divides A1 for some integer A1, but then we're done. There's nothing to show. And so there is nothing to show. So now, suppose that S of n holds for some positive integer n. And so we're going to consider the case where we have P divides a product A1, A2 all the way to A sub n plus 1. So now suppose that P divides A1, A2 all the way to A sub n, and then A sub n plus 1, where each A sub j is an integer. Now we want to use the induction hypothesis. And so what we are going to do is consider each of these, this whole product, as a product of only two numbers. And so let's let capital A be the product A1, A2, all the way through A sub n. And B is just going to be A sub n plus 1. Then P divides A times B. And then by Euclid's lemma, P divides A, or P divides B. But in the case of B, it just divides A sub n plus 1. If P divides A sub n plus 1, then we're done. So let us suppose that P divides A. And to suppose that P divides A, then P divides the product A1, A2 all the way to A sub n. But now we use the fact that the induction hypothesis holds for n, for when P divides a product of n integers. So by the induction hypothesis, we get that P divides A sub j for some j, and now this j is going to be in the set 1, 2 all the way through n. And so that finishes it off, because now we have P divides A sub n plus 1, or P divides A sub j, where j is between 1 and n. And so this shows that S of n plus 1 is true, and thus the theorem holds by the principle of mathematical induction. And we're done. And with this, we can now prove the fundamental theorem of arithmetic. That was the last building block we needed. So let's go ahead and get started. So this is a uniqueness and existence theorem because we have for every integer greater than 1, there are unique prime numbers p1, p2 all the way through pk, such that p1 is less than or equal to p2, less than or equal to p sub k, and then is equal to the product p1, p2 through p sub k. But we've already proven the existence portion back in section 6.4. And so by theorem 6.4.2, we have that every integer n, which is greater than 1, is equal to a prime or is equal to a product of primes. And so it suffices to show uniqueness. And so to this end, we're going to do induction. So we're going to let the statement, so let S of n be the statement, and more precisely, let me rewrite this as for each integer n greater than 1, and so for each integer n greater than 1, let S of n be the statement. And so the statement is there are unique prime numbers p sub j such that n is equal to p1, p2, all the way until we get to some p sub k. Now, notice that in the way that I'm writing this, it's slightly different because I'm not doing the ordering. I'm going to come back to the ordering at the very end once we establish that we have a unique factorization. So we proceed by strong induction. And so observe that when n is equal to 2, there is nothing to show since 2 is prime. And of course, if it's prime, and then we know from 2, that's the unique factorization of 2 is just 2. And so we're done. So S of 2 holds. Now, suppose that S of t is true for all t's within the interval 2 is less than or equal to t, which is strictly less than n. And so this is our inductive step, and we want to show that S of n is true. So we now use theorem 6.4.2. So by theorem 6.4.2, there are prime numbers let's call them P1, P2, all the way to some P sub m. And then we also have Q1, Q2, all the way through some Q sub r. Such that n is equal to the product of P1, P2, all the way to P sub n, And that in turn is equal to the q1, q2, all the way through q sub r. And so here's what we're doing. Theorem 642 tells us that every number is prime or is equal to a product of primes. And so we are supposing that we have two such prime decompositions of n. So we are writing n as a product of primes in two different ways. And what we want to show is that this is unique, that the primes appearing are unique. So in other words, P1 occurs in this list somewhere. It could be equal to Q1, but it could also be equal to, say, Q sub 5. The main thing is we want to show that they are all unique. And so P1 is equal to one of these, P2 is equal to one of these, so on and so forth. But here's where Theorem 724 comes in. By Theorem 724, we have that if P divides a product of numbers a1, a2 through a sub k, then P must divide one of those. And so we're going to focus on P1. P1 now divides Q1, Q2 through Q sub r. And so by Theorem 724, P1 divides Q sub j for some j in the interval 1, 2 through r. And now we're going to do a relabeling. So relabeling if necessary. We may assume that P1 divides Q sub 1. And so here's what this means. We know that P1 divides one of these prime numbers. Well, if it divided Q sub 5, just swap Q1 with Q5, and so we relabel the primes that we have listed, and so now our Q5 is now Q1. And so we may assume that P1 divides Q1. Since Q1 is prime, we deduce that P1 is equal to Q1. Since P1 is not equal to 1, and so P1 divides a prime number, the only numbers that divide a prime number are 1 in itself. So if P1 divides Q1, and since P1 is not equal to 1, it must be the case that Q1 is equal to P1. And so we got this here. The next thing we're going to do is divide both sides by P1. And so now observe that if we divide n by P1, that becomes P2, P3, all the way until we get to P sub m. But now that will result in also dividing this by P1, but we have now established that P1 is equal to Q1. So the right-hand side becomes Q2, Q3, all the way through Q sub r. And since P1 is prime, we get the following. Since P1 is greater than 1, since it is prime, we have that 2 is less than n over P sub 1, which is strictly less than n. But that means that our induction hypothesis does apply. And so now we apply our induction hypothesis to n over P1. And since, so by our induction hypothesis, S of n over P1 is true, and therefore P2, P3 through Pm equals Q2, Q3 through QR are the same prime factorization of n over P1. Because our induction hypothesis asserts that if we have a number less than n and greater than 2, well, greater than or equal to 2, then what we get, oops, and I just realized that should be a less than or equal to, then what we get is that these two prime factorizations are the same since we have uniqueness by our induction hypothesis. But that means that we must have the same number of primes appearing on the left as we do on the right. So in particular, M must be equal to R, and each P sub j must be equal to some Q sub k. For some k. So relabeling if necessary, we may assume that P sub j is equal to Q sub j for now j in index in the set 2, 3 all the way through m. But now we are done. That's exactly what we wanted to show, since now that tells us that the factorization for n is unique. And so now we come back to the factorization we had for n, and now this is the same. So consequently, S of n is true, and by strong induction, we conclude that S of n is true for each integer n greater than or equal to 2. And now to finish it off, we still need to show this inequality here. And so by the above, so now let n be an integer greater than 2. So I'm going to put here greater than or equal to 2. By the above, there are unique prime numbers P1, P2, all the way through P sub k, such that n is equal to P1, P2, all the way through P sub k. And now we do another relabeling. So relabeling, if necessary, we deduce that we can do an ordering, P1 less than or equal to P2, which is in turn is less than or equal to P3, and then we just continue until we get to P sub k. And that is what we wanted to show, and so we're done. And so the main thing in the last step is, we know that we have a prime factorization, P1, P2, all the way to Pk, but of course P1 may be greater than Pk. If it is, these are positive integers, greater than 2, so we just, greater than or equal to 2, so we can just rearrange them, change the labels, so that the least number is P1. Then the next least number, or possibly the same number, is the next one. And so we can do this. And that's it. We have proven the fundamental theorem of arithmetic. And so what we are going to do now is prove some consequences that the fundamental theorem of arithmetic implies. To ease notation, before we discuss our next result, let us consider the number 126,000. According to the fundamental theorem of arithmetic, this has a unique prime factorization. And we can go through and then see that this is equal to 2 times 2 times 2. And then we're going to have 3 times 3. And then we're going to have 5 times 5 times 5. And then finally 7. But now we want to be lazy. We want to collect the exponents. And so we have that this is equal to 2 to the 4th times 3 squared times 5 cubed times 7. And so now I'm going to introduce the following notation. So let n be an integer greater than 1 by the fundamental theorem of arithmetic, which I'm going to abbreviate to FTA, n has a unique prime factorization. And moreover, after collecting exponents, and so actually that's not the right phrase, but after simplifying the expression, the prime factorization we may assume that n is equal to p1 to the e1, p2 to the e2, all the way until we get to some p sub k to the ek, where each p sub j is a distinct prime. And in the same way that in calculus, when we talked about infinite series, when we had a bunch of terms being added, we introduced a notation n from 0 to infinity, or the n equals 0 to some 4. We have a similar symbol, the product. And so we can label this as the product from j is equal to 1 through k of p sub j to the e sub j. And so this is read product from j is equal to 1 to k of p sub j to the e sub j. And so this is the notation that I will be using for the remainder of the lesson, as it allows us to compactify the prime factorization that the fundamental theorem of arithmetic asserts. And so our next result is that if we have a positive integer n greater than 1, and we let n be the product from j is equal to 1 to k, p sub j to the a sub j be its prime factorization, with each p sub j denoting a distinct prime, then a natural number d divides n if and only if d is equal to this product, j is equal to 1 to k, and then the key thing is p sub j to the b sub j, where each b sub j is in the satisfies the inequality that it's greater than or equal to 0, and it is less than or equal to a sub j. So let's prove this. So we're going to prove the forward direction first. So let us suppose that d divides n. If d divides n, then by definition, there exists some integer, say m, and so n is positive, d is positive, so there exists a positive integer m, such that d times m is equal to n. And now we're going to consider the prime factorizations of both d and m. So by the fundamental theorem of arithmetic, and so I'm going to again abbreviate this as FTA, d and m factor uniquely into primes, and so let d, and so we're going to call the prime factorization of d the product v1, v2, and let's say that this goes all the way to some v sub s. And similarly, we're going to take m to also be a product of primes, and we're going to go ahead and in this case label these primes by w1, w2, all the way until we get to say some w sub t. Be the unique prime factorizations with each v1, actually with each v sub j and w sub j being a prime number. And it's actually where each v sub j and w sub j is a prime number. Then n, which is equal to the product from j is equal to 1 to k of p sub j to the a sub j, is equal to m times d, which is now equal to w1, w2, all the way to w sub t, and then we have v1, v2, all the way until we get to v sub s. And the fundamental theorem of arithmetic comes in once more. It tells us that this factorization must be exactly the one here. So by the fundamental theorem of arithmetic, we have that there are at most a sub j occurrences of p sub j in the factorization w1, w2, wt, then v1, v2, v sub s. And so if there are at most a sub j copies of some p sub j, this is telling us that this here must be equal to this here, but after rearranging, we have the following. So in particular, we get that d must be equal to the product from j is equal to 1 to k, and then we have p sub j to the v sub j. M is equal to the product of j is equal to 1 to k, and now we have p sub j to the c sub j, and consequently we have that n, which is equal to m times d, is equal to the product of from j is equal to 1 to k, and then we collect the like terms, so in this case the primes occurring in the factorizations, and so by exponent rules we have b sub j to the c sub j. But then that exponent must be exactly the one that we had earlier, and so we get that b sub j, that this here is the same as a sub j. So in particular, so hence b sub j is of course going to be less than or equal to v sub j plus c sub j, which is equal to a sub j. But now, it may have been the case that there is no prime p sub j occurring in this prime factorization for d, in which case the b sub j is 0. And so the exponents are between 0 and a sub j, but that's what we wanted to show. And so that finishes it off for the forward direction. So now let us do the converse. And so now let us suppose that d is equal to the product from 1 to k, p sub j to the v sub j, with 0 less than or equal to v sub j, less than or equal to a sub j for each j. And so now what we are going to do is consider the following. So observe that n is equal to the product from j is equal to 1 to k, p sub j to the a sub j, but this is equal to the product of j is equal to 1 to k, p sub j to the b sub j, and then over here we're going to put in the product j is equal to 1 to k, and then we're going to have p to the j, but now we're going to have a to the j minus b sub j. And so here we're using the fact that each of the p sub j's are distinct. And so when we multiply both of these, the exponents will match up, and so we're going to have b sub j plus aj minus b sub j's. The b sub j's cancel, and so we have that this here is a factor of this. If this here is at least 0. And so we're still not done, because it may be the case that this thing that we have here is not an integer. And so we got this here. And so now we use the inequality. Since a sub j minus b sub j is greater than or equal to 0, we have that m, which is now the product from 1 through k, p sub j to the aj minus b sub j, is an integer, since all the exponents are going to be non-negative. So therefore, d divides n. And that's what we wanted to prove, that d divides n. So we are done with the proof of this proposition. So as a consequence, we get the following corollary, which tells us that if n is a positive integer with its prime factorization being the product from 1 through k, pj to the aj, where each p sub j is distinct, then the total number of positive factors that n has is equal to the product from 1 through k of the a sub j's plus 1s. And so the proof is going to be quite automatic from the fundamental theorem and the proposition. So the way we're going to go about this is by letting d be some factor of n. So let d divide n. By the proposition, and so what I'm calling proposition 1.5.2, d is equal to the product from 1 through k, p sub j to the v sub j, where 0 is less than or equal to vj, less than or equal to a sub j for each j. In particular, there are a sub j plus 1 choices for b sub j for each j. And since there are kj's, we end up getting that the total number of factors is given by this. And so consequently, the total number of positive factors of n is equal to the product we want. And so for every index j, we have a sub j plus 1 choices, and we just take the product over all of these, and we get the statement. And so now we have the total number of factors for any positive integer n. And so let us return back to the example we had earlier. We had 126,000. We have its prime factorization as 2 to the 4 times 3 squared times 5 cubed times 7. According to the corollary, the total number of factors is attained by just taking, for every prime, look at its exponent, so 4 plus 1. So there's 4 plus 1 choices for what power of 2 we have, dividing our 126,000. Then we look at 3 squared. We have 3 choices for the exponent at 3 that the factor may have. And then similarly, 3 plus 1, and then finally for 7, 1 plus 1. So we have a total of 120 distinct positive factors for 126,000. So now we're going to prove the following lemma. Let r and s be positive integers. If s squared divides r squared, then we want to prove that s must divide r. So here's the proof. So what we're going to do, so let p1, p2, through p sub r, actually p sub k, be the distinct primes occurring in the prime factorization of the product of r times s. And so here's what I mean by this. Let me do a quick example over here. So let's say that r is equal to, say, 6, so 2 times 3. And let's say that s is equal to, say, 8. Actually, let's say that this is equal to 10, so 2 times 5. So in this situation, I'm looking at the prime factors appearing in the product of r times s. And so if we take r times s, this is going to be 2 squared times 3 times 5. So we're going to get 60. But now I only want to look at the distinct primes. So 2, 3, and 5. And so we're going to have p1, p2, and p3. And so we have the primes of r times s are p1, p2 through pk. So then r is equal, let me do s first. So s is going to be equal to the product from j is equal to 1 to k. And then we have p sub j, and we're going to raise this to, the exponent will be a sub j. And let us take r to then be j is equal to 1 through k, and p sub j to the b sub j, where we have that 0 is that the aj's and bj's are non-negative, where the a sub j's and b sub j's are non-negative integers. And so this is where it's different than the fundamental theorem of arithmetic and the notation I introduced earlier, because we are allowing for the possibility that 0 could be an exponent. And we see that in our example over here with r being 6 and s being 10. According to the notation we have, we would then write 6 as 2 times 3 as 2 to the 1, 3 to the 1, but then 5 to the 0. And then we're going to have, for 10, we're going to have 2 to the 1 times 3 to the 0 times 5 to the 1. But the main thing is we have all the distinct primes occurring in r times s. So let us continue. So now we're going to square both sides. So square the s and the r. Now observe, or then s squared is going to be the product from 1 through k, and if we square it, then it's just going to result in the exponent being doubled, and r squared is equal to the product from 1 through k, and similarly, now we have 2 times b sub j. But by assumption, we have that that s squared divides r squared, and now we use the proposition, because the proposition tells us what happens when we have a divisor of some number. And so in this case, s squared is playing the role that d had over here. And so we get that since this is a factor, since this divides r squared, 2 to the aj has to be at most 2 times b sub j for each j. And so by proposition 1.5.2, we have that 2 to the aj is at most 2 times b sub j for each j, and consequently, and in fact we have a 0 less than or equal to here, and so consequently 0 is less than or equal to a sub j, which is less than or equal to b sub j. And then we apply the proposition once more, because now applying the proposition to the fact that aj is less than or equal to bj for each j tells us that s divides r. And so applying proposition 1.5.2 once more yields that s divides r. And that finishes the proof. And again, now we're using the converse. Since we have that each of the aj's are less than or equal to the bj's, then we get that s must divide r, since the primes that are occurring the same p sub j's in the way that we set this up. So we got this. And now we can prove that every integer that is not a perfect square is a irrational number. So let us prove this. So by way of contradiction, and we're going to be doing exactly the same thing we did for the square root of 2 and square root of 3. So by way of contradiction, suppose that the square root of n were a rational number. Then there are relatively prime integers, and in fact positive integers, since we're assuming that n here is a positive integer, a and b, such that the square root of n is equal to a over b. Then we get that multiplying b to both sides, we get b times the square root of n is equal to a. But then we square both sides and we get b squared times n is equal to a squared, which then tells us that b squared divides a squared. But then we get by lemma 152 that b divides a. And now b divides a, but we know that a and b are relatively prime. Since a and b are relatively prime, it is the case that b must be 1. But then, if b is equal to 1, we get that n is equal to a squared. But this is a contradiction, since n is not a perfect square, which contradicts the fact that n is not a perfect square. Thus, the square root of n is irrational. And we are done. So I just want to make a quick comment over here. So we have that b divides a, and so since a and b are relatively prime, the only common divisors between them is 1. But we also have b divides a, so technically I am using proposition 152, and so the only way that we can have this divisibility is if each of the exponents occurring in the prime factorization of b are exactly 0. And so that's what's being assumed in this case. And so now we are done with the theorem, and that is the last result we will for our course. And one thing to be mindful of, and this is a nice picture from the number theory book that I used in the winter, is that we've essentially, as we've gone through the course, been climbing through various levels of abstraction. So in what we just did, essentially building towards the proof of the fundamental theorem of arithmetic, we utilized the Wall ordering principle. And through the Wall ordering principle, which is equivalent to induction, we proved the division theorem. We also discussed in our last lesson the Euclidean algorithm. Now, the textbook talks about solving linear Diophantine equations. In reality, this here is very related to Bezout's lemma, but we did not have time to go into that. And so with Bezout's lemma, we proved Euclid's lemma. And then the fundamental property of primes that is mentioned here is that if p divides a product of numbers, it must divide one of them. And then finally we got from the fundamental theorem of arithmetic. And so we have climbed this mountain towards the fundamental theorem of arithmetic. And then it has Fermat's theorem off in the distance and another peak. But in our course, it was not the peak of Fermat's theorem that we climbed, but rather the peak of the foundations of set theory, building up to the proofs that Cantor did that formalized the study of infinite sets. And it was a difficult topic, and we did it in the span of just over 3 weeks. But these were controversial topics at the time, and as we have experienced through the homework, through the lecture, some of the things that we have been working with, especially with uncountable sets, lead to some counterintuitive arguments that at first glance seem like it should not hold. We've also encountered the axiom of choice, and most recently, you've had a video for the Banach-Tarski paradox. And so we have climbed these various levels of abstraction and conquered them. And as you go through each of your math courses, you're essentially climbing a peak of mathematical knowledge. As you go through the course, everything building on top of itself. And one of the things about this course is that we have wanted to do away with our reliance on intuition. Not to say that intuition is bad, it's key, but we want to make sure that we can follow the logic, and so let the logic guide our intuition to prove things. Because if at any point we make a flawed argument, since everything is building on itself, if something is wrong, the whole theory collapses on itself. And so that's what we want to avoid. So I hope that you have all had a great term, and as you go further into your math courses, you're going to be utilizing the various techniques that we did in our course, from direct proofs, proofs by contradiction, contrapositives. And so these are part of your tools and arsenals for your future courses.